Good day. This video is going to talk about congruences. If we let m be in z, which is m be an integer, a is congruent to b modulo m if there exists a k in z such that a minus b is equal to km. So this just means that a is congruent to b modulo m if there exists a k in z such that a minus b is equal to km. By divisibility, this directly translates to m divides a minus b. So you can actually see that a is congruent to b modulo m if there exists a k in z such that m divides a minus b. So let's consider some examples. This concept of congruence is directly linked to the concept of remainders. So if we are saying 19 is congruent to what? Modulo 7. We'll be trying to find the remainder when 19 is divided by 7. So this means that 19 is congruent to 5 modulo 7. So the question here was, what is the remainder when we divide 19 by 7? And we got 5. You can actually consider another example where we have 2k plus 1 is congruent to what? Modulo 2. As you can see that 2k plus 1 is an odd number, and all odd numbers when they are divided by 2, they leave a remainder of 1. So you can actually see that this one is actually congruent to 1 modulo 2. There is also a shorthand for this. We say a is congruent to b mod m, in this case, or a is congruent to b mod m, like this. So all these are just meaning one thing. I'm just going to take two random numbers. Let me test, let's say 100. I want to test it congruent. What is it congruent modulo? Let's take modulo 3. So the question here is, what do we get as a remainder if we divide 100 by 3? You can simply see that 3 can get into 99. So it gets into 100, it leaves a remainder of 1. So 100 is congruent to 1 mod 3. If you consider another set of numbers, 50 and 7. We want to see the remainder when we divide 50 by 7. Since we know that 7 times 7 is equal to 49, we can actually see that it leaves a remainder of 1 as well. So 50 is congruent to 1 mod 7. You can think of any other examples which you can apply this concept. Okay, let's now consider remainders or residues. Okay, for any given positive integer, we can find positive residues and negative residues. So, given n, which is a positive integer, the residues for n, let's say the set of residues of positive residues is such that, so for n now, we consider 0 is a remainder, 1, 2, up to n minus 1. This is actually coming from the fact that we know that maybe if we are considering a particular example, like 5, we know that if we are dividing by 5, there is no way the remainder can exceed 5. We get a remainder of 0, 1, 2, 3, up to 4. So our n is giving us the residue of 0 up to n minus 1. The negative residues, the set of negative residues are such that equal to 0, 1, minus 2, minus 3, up to minus n minus 1. How do we retrieve these negative residues? So for any given number, let's say for any given number which is a positive integer n, if we divide n and find a remainder of n minus 1 as the positive remainder, the negative remainder, which is similar to n minus 1, would be minus 1. And similarly, like if we find the positive remainder for division by n is n minus 2, the negative remainder here will be minus 2. So they just stretch up to, if we get 1 here, this one will be minus n minus 1. So these are negative remainders and these are positive remainders. Let's consider a particular example. On division by 5, the positive remainders are 0, 1, 2, 3, and 4. And the negative remainder, which corresponds to 1, is 5 minus 1. So the positive remainder, which corresponds to 1, will be 5, will be 1 minus 5, sorry. This one will be 0, 1 minus 5, 2 minus 5, 3 minus 5, and 4 minus 5, respectively. So 0 minus 4 minus 4 minus 3 minus 2 minus 1. So if we are now talking about congruences in terms of this remainder, we'll be just saying 0 is congruent to 0 mod 5, and 1 is congruent to minus 4 mod 5. Same applies with 2 is actually congruent to minus 3 mod 5. and 3 is congruent to minus 2 mod 5, and 4 is congruent to minus 1 mod 5. So these are the corresponding remainders. We are going to consider the theorems on congruences.